Hello everybody and welcome to my classroom. Today we will be investigating the world of gases and how to quantify a sample as it undergoes changes. We all interact with gases each and every day. If you don't think so, then you might want to take some deep breaths for a moment. But how do we describe these gases and the changes they undergo? Gases, like these oxygen molecules, take the shape of their container. They are in constant motion. But what if the container changes, getting bigger and bigger, or smaller and smaller? How does this impact the sample? Or what if I added more of it? What would change based on this increase in quantity? How would it compare if I took it away? Think about the air in the tires of your car, or your favorite bag of chips as it sits out in the sun, or even a gaseous sample on a hot plate. What would change about the gas? For this lesson, we are going to investigate the relationship between temperature, pressure, volume, and moles for a gas that is undergoing changes. The relationship between these variables is described by the four big gas laws and their founders, Avogadro, which we remember from the concept of the mole, and some new scientists, Boyle, Gabors Law, and Charles, each providing a crucial connection between the variables associated with a sample of gas. Lorenzo Romano Amadeo Carlo Avogadro, or Avogadro for short, has already graced us with his presence. If you recall, we introduced his constant, Avogadro's number, during our discussion of the mole. But where did this constant come from? It was originally related to the number of molecules or atoms present in a volume of gas at standard temperature and pressure. See, Avogadro wanted to know how volume was related to moles. For instance, take this sample of gas, which we have contained within a flexible boundary. Let's hold the pressure and temperature constant to focus on the relationship between volume and moles. If we double the size of the container, this increases the available space and thus the distance between these gaseous particles, which in turn increases the number of particles that can occupy the space. Now wait, I thought we were talking about moles, but we are. Remember, the mole is related to the number of particles. They are directly related, meaning that as the number of moles increases, so does the number of particles. Therefore, as the volume increases, so does the number of moles and the number of particles. Crazy, right? Mathematically, this looks something like this. Of course, assuming that pressure and temperature are held constant. However, this confuses many students because most don't think that directly related variables should be divided, but should be multiplied. However, let's take a look at an example that we started with. Here, I have an initial volume V1 and an initial number of moles N1. If I were to double the volume, that means the new volume is just twice the original. What then must happen to N1 to ensure that both sides must remain equal? I would have to double it as well. See that 2 over 2 is just like multiplying by 1, resulting in a valid equality. Graphically, this would mean that as the volume increases, so does the number of moles, and in turn the number of molecules. However, remember that you must maintain constant temperature and pressure. Our next scientist is Robert Boyle, a renowned chemist, physicist, and inventor. Boyle wanted to determine the relationship between pressure and volume. Let's check out our sample for the previous example. Except this time we want to keep the quantity of moles and temperature constant. What would happen to the pressure as we decrease the volume? The particles become closer because the amount of space has decreased. This results in an increase in collisions between the particles and the walls of the container. This is what we call pressure. The more collisions with the container, the higher the pressure. Or the fewer the collisions, the lower the pressure. If we think about this graphically, as the volume continues to decrease, the pressure continues to increase. This is what we call an indirect relationship, where one variable increases and the other decreases. This is mathematically expressed as two variables multiplied together. Remember that we are keeping the number of moles and temperature constant. Again, why multiplication? Let's look at another example, where we decide to double the original pressure. So now it is 2P1. What would have to happen to V1 for the equality to hold true? Exactly, we would need to halve the volume. This would result in a valid equality, assuming that N and P are held constant. Our next scientist, Joseph Louis Gay-Lussac, wanted to further explore the idea of pressure. This has been widely referred to as Gay-Lussac's law. For this illustration, we are going to keep the volume and number of moles constant. we're going to place our sample of gas on a heat source. As the temperature raises, what do you think happens to the pressure? You might have guessed it. Remember that temperature is the kinetic energy associated with the sample of molecules. Thus, as the temperature increases, the particles begin to move faster and faster. This results in more collisions with the container, which we call pressure. Therefore, an increase in temperature would result in an increase in pressure. This is a direct relationship, which means that it should appear as a ratio of one to the other, like Avogadro's law. Of course, this is only the case if volume and the number of moles remain constant. This is the first time that we have seen temperature in a gas law, and you might wonder if you can use the units interchangeably, like other variables. For instance, pressure could be in atmospheres, kilopascals, etc. The equation would remain true as long as P1 and P2 have the same units. However, temperature must always be in Kelvin for the law to hold true. This is because the Kelvin scale is absolute, meaning that a gas at 50 Kelvin has exactly double the energy as a gas at 25 Kelvin, which is not true for the Celsius scale. Thinking about it mathematically, it must be Kelvin because the Celsius scale could result in a gas at 0 degrees, which would create an equation with no solution where I'm dividing by 0. Therefore, don't forget, always use temperatures in Kelvin for gas law calculations. You can always convert your answer to Celsius later if needed. Our last law is Charles' law, which looked to describe the relationship between temperature and volume, while keeping the pressure and moles constant. Let's say we have our gas within a container, again with flexible sides. If we place the sample on a heat source, this would cause the temperature to increase and the kinetic energy of the molecules to increase, just like we discussed earlier. Therefore, this would result in more collisions with the container wall, which would result in an increase in pressure. However, if we want to keep that pressure constant, then the volume must increase so that the increase in collisions does not result in an increase in pressure, because now there's more surface area for the collisions to occur. This means that as the temperature increases, the volume increases, or a direct relationship, which you can probably guess the equation for. Remember that this is only true if the pressure and the number of moles are kept constant. Don't forget that you must ensure that the temperature used in the calculation is in Kelvin for the relationship to remain true. Now you know the four big gas laws: Avogadro, Boyle, Gabors, and Charles. You might have already noticed this, but each law explores the relationship between two variables, assuming the other two are held constant. For instance, Avogadro studied volume and number of moles, which means that he kept temperature and pressure constant. This will help you solve problems because all you need to do is determine which variables are changing and which are held constant. This will tell you what gas law to use to solve that problem. Check out my next video where we apply these laws to a set of problems. Thanks for tuning in.